Hello everyone, I'm Zhang from University of Florida, Department of Mechanical and Aerospace Engineering. My topic here today is prediction of long-range infrasound propagation from tornadoes based on new atmospheric boundary layer wind tunnel experiments. I'm glad to introduce my co-authors, and Dr. Stephen Miller is my advisor, my colleague Maria Ojeda from Department of Civil and Coastal Engineering, and her advisor, Dr. Gurley. First, we would like to express our gratitude to our funding agency, NOAA, and here is my outline for today's presentation. I will start with the background information, and I'm gonna briefly introduce the methodology we use for our program. And the major part of today's topic is our experiments conducted in the University of Florida boundary layer wind tunnel. We will go through our experiments from the setup to the test design, including the details of the acoustic and the turbulent measurement setup. After that, we're gonna demonstrate some of our experimental results, and we're also gonna show a demo case of our propagation solver with turbulent staggering attenuation. Finally, I'm gonna do the summary, conclusion, and field work. Let's start with the background. A lot of researchers confirmed that the tornado can generate an infrasound even an hour before it hits the ground. And we know that the infrasound can propagate hundreds of kilometers away without significant atmospheric attenuation. So we believe that an early warning system is feasible with infrasound monitor system. Our approach is a combination of acoustic ray tracing, generalized Burgers equation, and the turbulent attenuation mode. For the long-range propagation, we believe that the staggering can be considered as attenuation. And you can say on the right side are two photos taken by our partner from Texas Tech University. The first one is our infrasound recording devices deployed in the field, and the second one is a tornado captured by the recording system. And the tornado is 5 miles away from the measuring point. Here is a diagram of our program structure. There are two major parts of our program, as you can see, the numerical one and the experimental one. The numerical solver is built with two parts, the rotating solver and the propagation solver, along with a bunch of atmospheric modules. The core part of the solver is the propagation solver. As you can see here, it's capable of capturing the nonlinearity, turbulent effect, and attenuation and dispersion. The turbulent effect is a key factor of our research, so we conduct a series of experiments to evaluate it. We got some source and we tested in our anechoic chamber, and we propagate the sound source through the boundary layer wind tunnel. During tests, we collect the turbulent and acoustic data and use them to analyze the turbulent staggering effect. Okay, here is a methodology we use for our program. As you can see, the first is acoustic retracing. We use the acoustic retracing method from Gamewell to build our own retracing solver. And the propagation solver is a generalized Burgers equation solver, and you can see the equation here. On the left-hand side is the signal itself, and the first term on the right-hand side is the attenuation term, and we're going to modify it towards turbulent staggering attenuation, and the second term is a nonlinear term, and the third one is dispersion term. For the turbulent staggering, we use a lattice scattering attenuation coefficient with modification based on our latest experiments. As you can see, alpha here is the attenuation coefficient, and the AS here is the modification factor, and the rest of them is just the original lattice attenuation coefficient. Here is a boundary layer wind tunnel. On the left side is the wind tunnel view from the test section, and you can see at the middle bottom here is our microphone pointing to the upstream direction. There are 8 fans, as you can see in this figure, each of them with power of 56 kilowatts and can provide up to 30 meters per second wind. And at the bottom left here is an example of the ground element. By changing the ground element height and rotation, the wind tunnel can generate different boundary layer profiles. The right figure is the configuration of the boundary layer wind tunnel. The black notation is the internal configuration, and the yellow notation is the acoustical configuration. As you can see, the microphone and the speaker location has the yellow dot, and the total propagation distance is 22 meters. For the test, we change the elevation height, which is EL here, and it's the vertical height from the ground and the ground element height. For the turbulent test, we also measured 4 different X locations to get the developing turbulent statics. Here are the devices we use for our measurements. On the left side is a Grass 46BE quarter-inch free-field standard microphone set. And you can say an inflow nose cone is applied to this microphone to remove the microphone flow interaction. The microphone set is mounted on a bracket that can adjust a microphone height from ground to 1.2 meters. The right side figure is our flow measuring system. As you can see, it consists of 3 5-hole cobalt probe. Each of them can collect the 3-component velocity oscillation at 2 kHz sampling frequency. The test signal is a lumped sum of single cycle sine waves at 800 Hz, 1250 Hz, 1.6 kHz, and 2 kHz. The test signal is played by a commercial speaker. To get the accurate output of the speaker, we test our speaker in an anechoic chamber. On the left side is the results of the anechoic chamber test. As you can see here, the black signal is 800 Hz signal, and we can see some distortions in this signal, so we only use 800 signal as a reference and not include it into our final data set. The recorded signal from the boundary layer wind tunnel is shown on the right side. As you can see here, the first zooming plot is a period from 53 seconds to 65 seconds. And the next one is a zooming of this period, and it's a section that contains a single cycle sine wave and its reflections. I think this figure clearly shows the test signal structure. For each frequency, we play the identical single cycles for 36 times, and from the beginning of the signal, you can roughly recognize 5 different sections by the amplitude. For this section, it's 800 Hz signal, and this one is 1250 Hz signal, and this is 1.6 kHz signal. This is 2 kHz signal. At the end of the test signal, we play 4 high volume tones that remind us the signal is over. As the wind tunnel is now anechoic, we only use the first crest of the amplitude as our data, and this method avoids the reflections. Here is part of our experimental results. For higher wind speed, the background noise raises dramatically. The signal to noise ratio is around 0.229 when the mean velocity increased to 7.8 meters per second. To remove the background noise, we ensembled our 36 single cycles to get a clean signal. The left figure is an example of the ensemble signal. Different color here represent different wind speed. As you can see, this 1250 Hz signal is measured at EL equal to 740 millimeters, and the EH is 30 millimeters. And we can clearly see an amplitude drop with increasing wind speed. On the right figure, it's much obviously the amplitude of the first crest drop decreases with increasing wind speed. To analyze the turbulent effect, we use lattice staggering coefficient, which need the integral density and the turbulent kinetic energy to construct that coefficient. I know here is a lot of information in this slide that I hope you can follow me from the left top of the left side autocorrelation figure. So the title here represents the X location, which is the distance from the upstream measuring point to the microphone, and the X is time difference, and Y is the correlation coefficient. From this subplot, we can say with increasing wind speed, the integral time scale decreases. From the repass perspective, which is, as you can see, the X equal to 20 is in the near speaker location, and the X equal to 2 is near microphone location. And we can say clear length scale increasing with along the propagation rate path. The right figure is, as you can see, x here is the mean wind velocity, on y is TKE value. We can also focus on the first figure on the top left corner. We can clearly say a TKE drop with increasing elevation height, which follows the boundary layer theory. And when we look at the x direction variation, we can say the TKE drops significantly by looking at the y-axis from x equal to 20 to x equal to 2. Okay, so as we got the experimental data, we repeat the wind tunnel experiment with our numerical propagation solver with 1250 Hz signal, and use exactly identical turbulent statics obtained from the wind tunnel. In the left side figure, we observed a significant amplitude drop from 0.19 to 0.11 with mean wind velocity increasing from 0 to 9.27 meters per second. The right figure here is a comparison of our propagation solver results with experiments. We also show our first step of modification in this figure. We believe that lattice coefficient is larger compared to the experiment, and the reason may be that the scattered energy is not 100% out of the incident wave. So we use Tatarsky's mode to get back part of the scattered energy, which contribute to the increase of the amplitude here. Besides the wind channel test, we also test our solver with a CFD simulated tornado from Dr. Markowski of Penn State University. The lattice acoustic analogy is employed to get the sound source from tornado velocity field. As shown in this video, the vortex near 100 high causes major infrasound. The right side figure is a spectrum we obtained at 1 kilometer high and about 800 meters away from the center of the tornado. As you can see in this figure, the x is frequency and y is sound pressure level. Two characterized frequency at 6 and 7 Hz is captured, and we use this signal as our input for the propagation solver. And for the propagation solver, first we use the acoustic refrigerant solver to simulate the propagation in the Havana region. The sound source is set at 1 kilometer high, and the launching angle is 53 degrees for the eastward propagation and 58 degrees for the westward propagation. As you can see in the left figure, the black path is the repath connect the sound source and the receiver. So we input this repath data along with the path-dependent data like wind speed, temperature, humidity, length scale, and TKE into our propagation solver. And the right side figure is the output of the propagation solver. We can see here, along with the right one is the received signal, and the black signal is the original signal. We can say, besides the spherical decay, the dispersion and attenuation changes the waveform. Here is the summary and conclusion and future work. So first, I'm going to summarize our program. First, we conduct a series of wind tunnel experiments and analyze turbulent effect on the long-range propagation. And we also observed the turbulent attenuation and compared the attenuation with lattice coefficient. And we also integrate the turbulent attenuation coefficient into our propagation solver to account for turbulent effect. For the future, we can obtain higher fidelity models and calibrate our coefficient with experiment data. We're going to also integrate more atmospheric model into our numerical solver, and then we may also try to implement turbulent reflection models to our solver. Okay, that's the end of my presentation. Thank you for your attention, and I'm gonna take questions.